I don't know if you ever checked the recorded session, but I'm recording all of them. And it's like extra effort to upload, edit sometimes. Anyway, so today we're going to talk about design experiments, a little bit about correlations and R. So you just finished the project one, said let's go a little bit through the project two, sorry, and see what we did. So the main question basically that was asked in the end of almost in the end of the project two was, does the death penalty deter murder rate, right? That was the main things you were trying to find out what did your study. So in this particular case, we cannot do, for example, randomized controlled experiments that we were doing with our other data that we had, other tables. We cannot basically do this because we cannot, obviously we cannot have a society, divide them to half and say, okay, half of you start killing each other with death penalty, half of you don't basically kill each other, but we don't gonna put death penalty and then we study and see what's happening there. We cannot do this type of a study here. But what we can do instead is we can compare two groups that appear similar except for death penalty laws. That's why we look at these two periods in 1971 versus 1973, where the death penalty was eliminated for some period, then again reinitiated. So the following basically evidence was presented in part 234, that we knew that from 1971 to 1973 there were a lot of murder rate increase in that particular period, that there was no death penalty. And then from 75 to 77, there was a lot of murder rate decrease. That after, in that period, basically there are death penalty rules. So that's, I mean, having this, we were trying to basically conclude or to see if there is any correlations basically between death penalty law and basically murder rate. And from 1960 to 2003, estate murder rate increased about as often as they decrease over 2 years time span. So there was a lot of data over there, and some of them might be confusing. So we saw this in 42 years across 50 estates, there were only 45 more increase than decrease in the murder rate. So in this particular period, in this 42 years period, if you have 2 years interval, you can have 2100 different combination of increase and decrease. Okay, for example, increase, increase, decrease, increase, increase, or increase, decrease, increase, decrease. If you add all of them together in this period, in a 2 years interval, you can add up, you can get this 2100 possible combination of increase and decrease. But in that period, we only saw 45 more increase than decrease, which is, I mean, if you compare these two, they are a little bit, it's basically negligible. It's not a big number comparing this 45 increase if you compare it with all these 2100 possibilities of combination of increase and decrease. Then the cumulative difference in number of increase and number of decrease for state, we saw this. So if those basically increase and decrease happen totally randomly, we would see something like this in that period of 42 years, sorry. From 1960 to 2003, 2003, that's what I remember. So if it's happened totally randomly, you're gonna see something like this that's going up, down, and there is basically, it's totally random. You may see something like this, but still it doesn't make it any pattern on it. Still it's going up and down, it's fluctuate a lot. But what we have observed actually is something like this. In some period it went up, in some period it went down, up, a lot down. So you can see if you compare these two, basically, they are not equal or they are obviously different. So you can say this is not totally random. This is obviously not a random ups and down in the murder rate case. There are other factors basically involved here. Not that we know all of them, but we can obviously say it's not random. Just 1 year is more death murder. I mean murders, and 1 year low. So obviously these are not. So what we were seeing is this period basically 1973, somewhere like this, to 1975. So no, 71 to 75 that we were studying this this particular period. Then we were talking about initiating basically the murder, the death penalty without death penalty. Then we have this figure that shows from 1950 to 2001, comparing basically murder rate in United States versus murder rate in Canada. This is murder rate in United States. Basically, numbers is here per 100,000 residents, and this is the number for Canada. You can see in Canada in general, even in the peak, basically there are 2 point something. For United States in the peak there are 9 point something, okay, or 10 point, I don't know, 11 maybe. So you can see in general, United States has much more basically homicide comparing to Canada. But what is interesting here is this this particular period of the time that we were concentrating. This is when we have death penalty in the United States. In this particular 2 years, around 1971, in this particular period, it is abolished, the rule, okay? That's why we saw it's went up, went down again at some period. Then from here, it's again reestablished the death penalty. So why we comparing basically United States with Canada is because they are two different countries. They are totally having dependent judicial systems, so they are not affecting each other. So what I'm trying to say here is, first of all, you tell me what did you concluded? I don't remember all of them. What most of you concluded that is there any, basically the death penalty deters the murder rate or not? What did you find out in your, some of you share your finding? Jose Chosa? You remember project 2 final? What did you conclude? Does it change? Basically, does the death penalty increase the murder rate or decrease the murder rate?
I don't remember right now, but I can access my OKPy to check my answer.
Okay, no worries. So the idea is here is, if you had this this graph, you could say that the increase or decrease in the murder rate, particularly seeing this period of time, is not totally depend on that basically death penalty, to have death penalty or not, okay? Because you can see even in that period in the Canada that they had death penalty in this period of time, but they don't have the death penalty in this period of the time. Still the murder rate is, the pattern is more or less the same. There are some increase here, there's some decrease here. So it's not totally depend on how to say, the homicide rate was not totally depend on having the death penalty or not. If you had this figure, basically you could conclude totally different things, okay? So I'm not trying to basically abolish all the things that you concluded just by this figure, but the point is here is we need to do some, how to say, some more visualization maybe to conclude, to come up with a better conclusion. So that is from project 2 that we observed at the end of the project 2. So let's recap what we did in the last class. If you remember last class, we did some questions like this. We answered some questions like this based on the central limit theorem and Chebyshev inequality rule that we knew. We could answer this type of questions. So let's see what we were studying. So we said if you have a if we fix a large sample size, draw all possible random samples of that size, compute the mean, then you end up with a lot of mean that they can basically form your probability distribution of the sample mean. And we knew that's going to roughly look like a normal distribution. Those are the things we saw last two classes with a lot of examples. So basically that roughly normal distribution that you're going to see if you calculate this, you basically study, you get, you take a sample, you take the mean, you take another sample mean, and you add them up, and you, if you did a histogram, then you would add up with, you would end up with a, how to say, a roughly normal distribution that's centered at the population mean. Then we see that there is an inverse relationship between your standard deviation of this distribution with the sample size. The bigger sample size you take, the lower standard deviation would be. You remember that was what we calculated the last time. So what we want to do now is to answer this question. We want to estimate the average compensation for San Francisco public workers, the table that we saw before. So we want to know how many people should you sample at random in order to get 95% confidence interval with a width of $10,000 or less. Can you answer this question? So just see what we're trying to do. We want to calculate basically average compensation or average salary of all the public workers in San Francisco. And we want to get that 95% confidence interval, that the width of this confidence interval is just 10,000 or less. Because, for example, I can say by more than 95% sure that all these public workers, like 95% confidence sure that most of the public workers in San Francisco are getting somewhere between $10 to $1 million per year. Of course, that can be 99% sure that is true, but that doesn't tell us anything, right? That doesn't give us any useful information. So we want to do this, and we want to get this width for our confidence interval. So we can say by 95% confidence that like most of the San Francisco, basically public workers get this period of this intervals of salary per year. So let's see what we have here. So this is the table that we saw before. So here we have basically the organization, public workers in, like, for example, transport, commerce. The job title is water quality, 1, 2, total compensation or salary per year, plus benefits are this 1,700 here in this case 41,000, in this case 110,000. So these are all the salaries per year for all the public workers in San Francisco. You can see these are basically all of them. We have all the population here, okay? This table is including all the population. So if we do the histogram, you remember we saw that something like this, that most of them are falling between 100K to 200, maybe 20, 30Ks per year salary. And there were some weird, not weird, but there were some, I don't remember exactly what was their title, but some people that earning like 600 plus salary per year. So this is what we did here. This is all our This is all our total population, okay? So the question is this, okay? We want to get this width in our confidence interval, 95% confidence interval. So this is, I'm going to use these two functions that we defined before here too, to calculate the bootstrap means and then see their confidence interval. So if I run this, so if I take 200 samples here, I'm taking from my population, which is this, 200 samples. So the point here to remember, to pay attention is, I'm assuming this is my population, okay, but I assume I don't have it, okay. I'm going out in San Francisco in this street. I take 200 people randomly, and then I ask them their basically, let's say, total compensation per year. Then I add up, I make this table from that 200 samples. So if I do the bootstrap here, you end up with this. So this is what we got, okay? So I get the 200 samples. This is my 95% confidence interval. And let's see what is the width of the confidence interval. If we diffract these two numbers, this is the width I get, okay? 18,078. This is totally different with that 10,000 that I was aiming at the beginning. So you know there was an inverse relationship between, let me show you again this. There was this inverse relationship between my standard deviation and my sample size. So this sample size that I took in my experiment right now was 200. So what should I do in order to end up with this width? Now my width is 18,000, which is much bigger than what I'm expecting. So any insight? So what should I do? How should I change my sample size? So if I take another sample, I'm going to end up with this. This is the width of my next, my basically sample, 17,000. So you can say the first try I did, I was 18,000. With the same sample size, 200, I get 17,000. It's fluctuate around like 18, 17, 19. So what should I do in order to have it in the width of 10,000?
Increase the sample size to around 900, I think.
900?
Yes.
Let's see. So why you said 900?
Well, when calculating with the sample size, we are diminishing the standard deviation we get as a result. With a sample size of 200, we are basically dividing the standard deviation we get to around by around 15.
Mm-hmm.
So if we want around half of that, we must double that 15, so 30, and the square of 30 is 900.
Or there was an easier way, if you could say, okay, the first try I'm doing with 200, right? This is my 200 samples, and I end up with 17,000, right? So if I increase my sample size, by 4, a square root of 4 is going to be 2. So my width is going to drop by half, right? So it was like 17 here. I'm expecting to see if I make it basically 4 times bigger, I'm expecting to see half of it. So let me go first 800. and see what I'm gonna see. So this is the interval I got. If I drag this to number, oops. I get around 8,700-ish, which is satisfying my conditions, right? So that's what we could do here. You can get a sample and see what's happening here. So you get 18,000. So I know if I if I basically multiply my sample by 4, because I'm calculating the square root of it in that equation, I'm going to end up with half of this. If I go 900, it's going to be much lower, of course. So if this is 900, so it's of course it's lower. Okay. So that's what we could do. Okay, let's go back to the slides. So what I did here, I take the 200 samples, I calculated, then I see no, it doesn't satisfy. It's like two times the range that I want. Okay, the width that I want. So I basically I increase my sample rate to satisfy these conditions. So let's talk about choosing a sample size. So we know this central limit theorem says that the distribution of a sample mean is roughly normal, centered at population mean. This is what we learned from central limit theorem. So 95% confidence interval, if you remember Chebyshev rule, inequality rules, it's centered around minus plus 2 standard deviation of the sample mean. Because why this is the case? Because it is a roughly normal distribution. If you remember, for Chebyshev inequality rule, we had 2 different conditions for all type of basically distribution, and there was one for normal distribution or roughly normal distribution. So this is exactly like that. If you consider 95 confidence interval, it's exactly, it's like looking at your mean, sample mean plus minus 2 standard deviation away from sample mean. You get 95% confidence interval. So the total width would be around 400, around 4 standard deviation of your sample mean, minus 2 all the way to plus 2 from your sample mean, which would give you 4 standard deviation. So I'm missing something here. So what we did, okay, if you remember this, what we did with that San Francisco public workers example was we have to take a sample before we can decide how big of a sample we need. But that's not the case that we can do really in the real world. You not get this, how to say, leverage always to go take 500 samples, come back to your study and say, oh, now I know I need 2,000 samples, okay? I'm going out to do another 2,000. You may do that sometimes, but that's not the case for all the things that we do. So that was the problem with San Francisco workers, and that problem exists because we didn't know the average, basically. We didn't know the standard deviation of all our population. That's why we needed to do the first, first sample, then to study that and see what's happening. Another point to remember is we aren't guaranteed that our interval will be as narrow as we want, because as you see, each time you take that certain number of samples, you're going to get some basically interval that doesn't necessarily would be fixed. For example, you say, for sure I want 10,000. That doesn't happen, because each time you do, you're going to fluctuate around 10,000. You're going to maybe go a little bit upper, a little bit lower, but not exactly the same. So we never get as narrow as we want, okay? But it gets close to that we do. So how we can address this issue? Well, we're going to address that with this discussion question. So we want to see what we can do about that. Okay, as I mentioned, you don't get this chance to do sometimes 2 times sampling, and also you don't know, you cannot guarantee this interval. So let's look at this sample or these questions. We want to estimate what % of voters will vote for candidate A in an upcoming election. So this is an election, country, whatever, cities, society. And we want to know there are 2, for example, candidate A and B. We want to know what % of voters will vote for candidate A. So how many opinions should you sample at random in order to get 95% confidence intervals with a weight of 3% or less? This is slightly different with what we did for San Francisco case. In there, we wanted this weight to be $10,000. Here we are talking about the proportion, not certain number. Proportion of the voters. That basically with 3% or less the width of our 95% confidence interval, that certain number of people going to vote for candidate A. So in order to answer these questions, okay, this is the same thing that we saw. So we saw this, right? Total weight is for a standard deviation. That was missing the first slide. So if basically this is the equation that I have, right? I want my 4 times my standard deviation divided by basically square root of my sample size. The same equation, I just changed the place. So in order to control the width, suppose you're okay in that example, you are okay with the width being 3%. Okay, let me show you something before telling this. Look at this here. So imagine this is my voters, and this is here, for example, 9 people going to vote for candidate A, 1 going to not vote for candidate A, going to vote for candidate B. For example, if I calculate the standard deviation for this population that I have here, I'm going to get 0.03. What if this is 0? So what if 8% basically voting for candidate A? I'm going to get this. Of course, if all voting for candidate A, the standard deviation would be 0. That's for uniform distribution. Of course, we get 0 always here. So if I go more people voting for candidate, less people voting for candidate A, I'm going to get this standard deviation. Let's see, half of half. I'm going to get 0.5 more. I'm going to get this. I'm getting this. I'm getting this. I'm getting this. So what you're observing here is our standard deviation never went above 0.5, right? Did you see that? In this type of case, when we have only 0-1 distribution or yes or no distribution, or when your basically data include only 0 and 1, you can make sure in the worst case, your standard deviation never goes beyond 0.5, as I show you here. It can go all the way from 0 to top from 0.5. It never goes beyond that. So we have basically the maximum level of standard deviation here. So in that example, we are saying we want our width to be 3%. So basically, this is what we want to satisfy our calculation. We want to satisfy this. So this is equal with this, right? I mean, this is basic math. From this, I can get this. So basically, a square root of my sample size should be bigger than 4 times standard deviation divided by 0.03. Is there any questions here? Any confusion? So this is basically a thing that I want to calculate. So let's see what we can see in the code in the demo. So we have the top basically in this part in the case of San Francisco public workers, we don't know the standard deviation of our population for their salaries. For this example of voting, we know a standard deviation of my population in the worst case possible, it doesn't go beyond 0.5. So I can just consider this standard deviation for my calculation. So now I have the equation to calculate my sample size. Exactly, I can know what sample size I want. So this is not the case anymore. I'm not going to sample once and see what's happening for my standard deviation, go another samples to have that width that I want. Here I can say my worst standard deviation for my population is 0.5 because we see it never goes beyond that. So this is the width of a standard deviation, which is 4 for 95% of normal distribution. As we said, it should be mean plus minus 2 standard deviation. So this is the desired width that I want, 3%. So basically, I put that, I calculate my sample size as you see in the equation. My sample size is equal to my worst standard deviation that I have, my standard deviation of population that I have here, 0.5, multiply width in the standard deviation divided by desired widths, all to the power of 2 in order to have my sample size. So if I do my sample size, I'm going to get this 4,444.444. So this can be round to 4,445 basically samples. Is there, did you get what I'm doing, what I'm trying to say? Any questions about what I did here?
Can you explain again that part, the last one you did?
So here, what we want to do, let me go to the equation. We know this equation exists, right? Based on this rule that we have about central limit theorem and Chebyshev inequality tells us that if you have your roughly normal distribution and you go plus 2 standard deviation minus 2 standard deviation, 95% of your data going to be in that interval from your mean plus 2 standard deviation minus 2 standard deviation. So this is my 95% of confidence interval would be this. Based on this. This is the same thing that we did, we saw before. My standard deviation here is equal to 4 times the standard deviation of my population divided by sample size. So that's basically, and that can lead us to this equation because that 3% is the condition that we have. We want this, basically we want this to be smaller than this 3%. That's the thing that I'm asking in this question here. So I want to know how many opinions should I sample in random in my country or my city to know how many people are going to vote for candidate A with 95% confidence interval, and the width of that I want to be less than 3%. Okay. So knowing this, you put that in the equation. Now you get this. So basically, your sample size equal to all this to the power of 2, right? If you remove this square root here. So now I have this 4. Of course, this is a fixed. Now I know this. This is, I said in the worst case, it will be 0.5. And I have this number. So that's why I can exactly calculate my sample size. So that's what I'm doing in that in here. So I have my that 5%, which is my standard deviation of population in the worst case possible. I have this 4, which is width of the standard deviation. I have this desired width. Those are the numbers that I'm putting in this equation to calculate my sample size. So I end up with this sample size, 4,444, or I can round it to 4,445. So what I'm saying now, with this number, I should definitely get 95% confidence interval with less than 3% width, right?
Okay, thanks.
So that's basically what we see here. We knew this is smaller. In the worst case, this standard deviation is smaller than 0.5, so I can calculate my sample size. So let's see whether it really satisfied the condition or not. So this is the samples I take from my population. I ran some codes earlier before you see, because I don't want you to see that. So just consider I went out in the city. I sampled 4,445 people, and I asked them who is they going to vote for. So some people tell me A, some people go to candidate B, candidate B, candidate A, candidate B. So this is my samples from my population. Okay, so I want to now calculate. Okay, here. So what I'm doing here basically is just calculating this percentile 2.5% from my observed samples. I'm sampling from my observed samples. I put in resamples, and I'm doing that 1,000 times, basically resampling. Doing the bootstrap from that, and then I'm getting this this basically interval. If I diffract them from each other, no. So I'm going to get 0.027. So you can see it exactly satisfies the condition that I have to get to get the width with 3%. 3% width with my confidence interval. This is the same thing that I'm doing here. I'm calculating the percentile. The lowest 2.5%, the highest basically 2.5%, this last 2.5% this side, 2.5% this side. And if I diffract that, this is my basically the width of my 95% confidence interval. Okay. This is any questions? Basically, this is the mean I get from that 1,000 samples. Okay. So I'm doing that 1,000 times. I'm getting all these numbers. That these are basically okay. What it tells us this number, this means number. This means 30% going to vote for candidate A here in another resample, like resampling from my sample. I'm not going back to the population. I'm going back to my samples. I resample from my sample. If you remember that, then I do another 29% going to vote for a candidate. I find 28%, 30%, 29%, 29%. So those are basically percentage that I'm getting. If I calculate this, basically percentile at the end, it might for 95% confidence interval, I end up with this, which is satisfying my conditions. Is it clear? So basically what I'm telling by 95%, I'm 95% sure candidate A going to receive between 31% of the votes, okay, to 28% of the votes. Candidate A going to get 31% to 28% votes from my population. And that's basically the table that I didn't show you earlier. This is the table that I defined. So you can see that's exactly satisfying this. So let's say this is the voting result at the end. Let's say this is the, I don't know, Democrat candidate in the United States. This is the Republican candidate. So I know this is what's going to happen. This is what my result told me. And this is what my prediction told me. Is that clear? Any questions, doubt about what we did here? No, I hope there is no questions. So I really wish everything is clear, or at least if there are questions you would ask. So if, yes.
So if in the code you change the A for B, it's going to show.
Pardon? Here?
Yes, the A for B.
I don't get
the letter A for the letter B.
No, candidate A get like 33%.
Like in the code in the bar above, it says that NP node 0, the sample column equals to A. If you change that part to B, it will show the.
If I change this one to B?
Yes.
Let's do it. I'm running it. So I get this. Okay. So if these are my means. So I get, I'm sampling my resampling my samples. I'm getting 70%, 71%, 69%. And if I drag this two, I should end up with the same result. 0.0226. Basically 2.56% is my weight, my interval weight. So it means by 95%, I guarantee candidate B here in this case, going to receive 71% to 68% of the votes. So you know what we are doing here. So if I say, okay, so how you predict this upcoming election, let's say it's a little bit easier when we are talking about United States because there are two candidates like Republican, Democrats. So now Trump against Biden. So what do you predict here? Okay, so I can tell you, for example, I'm 99% guarantee you that Trump going to receive between 2% to 98% of the votes. It doesn't help you at all. It doesn't give you any useful information. Of course, that satisfies with my condition, but it doesn't tell you any useful information. That's why we need to bring that width as much lower as possible. So if I tell you I'm 95% sure Trump would receive like 71 to 68% of the vote, then that gives you a very useful information, very useful or very precise predictions. Because that's my 95% confidence interval, and the interval width is very, very narrow. It's just 3%. I give you 3% basically possibility of error. So that's the idea what we are doing here. So if I go back to that equation, so you can see I could, in this particular example, that my data is bounded by 0, 1, or my population is bounded by 0, 1. I have just 0 and 1 in my population. I can calculate this because I know for sure a standard deviation of this 0, 1 population never goes beyond 0.5. So what it tells you basically, you can calculate, what you understand from this, it can be, if you sample, for example, for an election from 4,400 something people, most probably randomly, again, I highlight that, if you pick those samples totally randomly, considering all the possible factors, you're going to get very, very good rate on your prediction for the election. Or for anything that is like yes, no question, or voting, for example, yes, I vote, or no, I don't vote, right? For this type of population, 0-1 population. So let's have like 10 minutes break, and we come back by 11:10. We're going to talk about basically prediction. We're going to talk about correlation a little bit, okay? So we come back by 11:10.
Is there a way to do a similar kind of procedure with studies that don't involve a 0-1 study?
Exactly, yeah, you can do that. Anything.
For example, we were talking about elections, and in this case, the United States, like you said, fits the kind of problem we're looking for, because there's only two parties involved, the conservative part and the Republic party.
Right.
Yeah, but if we wanted to do a similar kind of study, for example, here in Mexico, where we have different like groups of people, PRI, PRD, PAN, how would we go about making a similar case? How would we obtain the worst case scenario STD?
Okay, what I think there are a little bit that's a little bit confusing talking about this, comparing that with that, but usually your worst standard deviation doesn't go most of the time. Okay, it's not a precise number, but most of the time your standard deviation doesn't go beyond half of your range of values. Okay, you can calculate here. If I put, for example, you say we have 4 different candidates in Mexico. Okay, let's say that. So we have all these options. Let's say candidate, like for example, candidate 4, candidate 3, 2, 1. So we can have, for example, here, let's say 3. Okay, so we have, let's say like 0, 1, 2, 3, right? So if you put 3 here, I don't know, let's say what it would be the standard deviation, but let's go 3, I don't know, just random, 2, 1, 0, 0, 0. Your standard, if you calculate this, your standard deviation in this example never going to go beyond 1.5. Even if I put all like 3, let's say 3, I'm just doing it. I can put I could make it a function. Or 0, 0, 0. Okay, it never goes beyond 1.5. So maybe you can calculate that 1.5 now, put that in your equation, and see what would be the population you need. So this would be 1.5 here, this one.
Okay, so it can be done.
It can be done with a good, very good.
Or is there a better way to do it?
I cannot think of a better way really to find the sample. We are talking about this, right? All here we are talking is about how many people I need to ask in order to make sure, right? In order to make sure I'm getting a good estimate. So I at the moment right now I cannot come up with a better solution for that than this. So you can see, let me put that and see what number we get. What would be that if we put that in the calculator? So 4 multiple 1.5 by 0.03. It would be 200 to the power of, it means 40,000. Okay, I get this.
Okay.
So it means I have to sample 40,000 people to get a good estimate of my voting, basically, predictions for 4 candidates.
Okay.
It sort of makes sense, right?
Oh yes, because we have more possibilities of the
More
choice.
possibilities, exactly. And the point is, it just didn't get 4 times bigger than this.
10
right?
times.
It's like 10 times bigger, almost,
Yeah.
right? So if you go perfectly, take a random sample from your society, 40,000, you're going to get a very good, basically, estimate.
Okay.
But if you notice, for example, something tricky is happening here. So most probably something you're going to see in the next few months when we get closer to the United States elections, there are going to be a lot of basically predictions coming out, and usually they have bigger number than this. And then you may wonder why they need to go that big in order to get this type of preciseness, okay? But the idea is sometimes they go beyond this because, how to say, to make sure they have enough randomness in that big number. You know, because here it need really to be a random, okay? For example, you come to the junction near Tech and you start asking people, maybe most of them going to be students, okay? Then you say, okay, most of them going to be educated people. So maybe then you're not gonna exactly get the like average of your society, okay?
There's like a bias on the
There would be a
population.
bias, right? So sometimes you go beyond this in order to make sure you have a good basically prediction. You have a good randomness in that.
Okay.
But in this controlled experiment that we can do in our PC, in our data, you can see it gives us exactly basically the data we want. This is the basically what I did here is I didn't show you. I defined this table earlier before you join class. This one, okay. Then I sample this. So basically, I sampled 4,000 from this, 4,445 from this, because that's the best we can do in that relation. But if I just tell you this is our population example, population sample, that's exactly my population sample. I end up with this, then I say, okay, now I see the voting results. This is my voting results. Unfortunately, Republican got 70% of votes. So that would be something like this.
Are we on break right now, Madi?
Yeah, we have 5 more minutes. We're going to start from 11:10.
Okay.
But anyway, I'm here if anyone has any questions about anything. Oh, I resume recording now. Sorry about that. So this was, okay, let me show you this again. So again, talking about this, the correlation coefficient is a numerical value measuring basically linear association between two variables. So did you get it? Any questions about this? Okay, so if you got it, so we have this 4 scatter plots, okay? And we have 4 different correlation coefficient or R values. So I want you to associate, you tell me, for example, a scatter plot A, which R belongs to scatter plot A?
Number 2 is related to A.
So Juan Salvador saying number 2 is belong to scatter plot A. And can you tell me why is that?
Because it's negative, because of the way the slope, the direction the slope is going, and since between both negatives A and C, A is less spreaded out, it must mean it has the higher R value.
Okay, yeah, that's perfect relationship. So Xian, can you tell me for scatter plot D?
Probably 3.
So you're saying
Because you have 2, the same reasoning. You have 2 that are positive, and between those, it is the one that is less related.
okay, perfect. Yeah, you're saying there are 2 positive, which is like a straight up line. This is maybe more how to say, there is more correlation here. So you say the higher value belong to this, the lower value belong to this, and as you said, Juan Salvador, there's 2 minus 2 relationship. This one belong to this because there is a correlation, but not that strong. That's why it's a lower number. Perfect. So what I show you there is just the definition, but how we can calculate it. We can have y in a standard unit, x in a standard unit. We get the product of x and y in a standard unit, and we get the average of it. So that gives us basically the R value. This R is basically the average of product of x in a standard unit and y in a standard unit. Product of these 2 numbers, basically. Like product. So it measures how clustered the scatter is around a straight line. Okay, that's the whole idea. So for example, this is our distribution, these are your dot. So you want to know how clustered they are around this straight line. So let's go back to see some demo of it. So here I have these x and y values. So if I do the scatter plot, this is what I see. It's a bit cloudy, but still there look like some relationship here, correlation between x and y. So let's convert them to the standard unit. So what I'm doing here, I'm convert them to the standard unit and I multiply them. I get the product of that. Then I put it in this table. So I have their x in this is my x and y, original x and y. This is x in a standard unit, y in a standard unit, and this is the product of them, basically x multiple y. So that's the equation, right? So get x in a standard unit, y in a standard unit, multiply them, get the product, and then calculate the mean of them, right? Average of this number. So this is the R value that I get for this distribution. As you expected, it's positive. So it's an upward correlation between x and y. So, okay. So basically that's what you see, something like this. Maybe not that exactly, maybe a bit lower, some sort of like this type of relationship. So you see it's a slightly upward because that's why it's a positive value. So let me do this. So I'm here, I'm defining just a function to do the correlations. get the basically standard unit, multiply standard unit x, standard unit y, and then get the mean and return that as my basically R value. So same thing, I get the same thing. So if I scatter plot the thing that we saw in acceleration, and you remember that SUV, acceleration versus the retail price, right? You see this? So what do you think I'm going to get here if I calculate the correlations or R value for these two number? R value for this scatter plot. It's going to be positive.
Around
It's gonna be positive for sure.
like a positive 5 or 6, maybe.
Yeah.
5 or 6?
0.5 or 0.6.
0.5 or around that. Let's see. Yes, it's getting exactly as you predicted. It's positive because it's a little bit upward, and it's not that strong correlation because it's cloudy. So you see a low correlation between these two values. And if I do that here, what do you expect to see?
Maybe like a negative 4 or 3. 0.4 or 0.3.
Negative
Yes,
0.4
more or
or
less.
3. So
Oh.
here we see negative 0.66. So there's more correlation here. And why is that? Is because especially for those like too far dots from the, basically if you draw a line here, you see there are certain dots that are too far, which make the correlation much lower. Here maybe they're a little bit less scattered if you consider let's say these two lines, they're less scattered, they're more inside this comparing what we saw in the previous one. That's why there's, of course, is negative relationship, negative correlations, and it's a bit higher correlation we're observing here. But another thing to remember here is we do this for just numerical values. Okay, we are calculating this just for numerical values, like this. Any questions about correlation coefficients or R? So, no, yes? No?
No.
Okay, so that's what we saw. Let me see what we missed in recording. Standard unit, correlation. Okay, good thing is we didn't miss much on recording. I was talking basically about prediction, about correlations between two values. So that's it from today. It's so remember this again. This is what you need to know, that it measures only linear association. If you see the R0, you cannot say that there is no association between these two variables. That only you can say there is no linear association. Okay, that's why they are uncorrelated linearly to each other. Is that clear?
Yes.
So perfect. That's all from today. If there is no questions, I'm going to close the session. Just to let you know, again, there are project trees available. The deadline for how to say, what's that? The checkpoint is in 2 weeks. Check it out. Okay. And the final deadline for final submission is in 1 month. Check the exact date and hour, please. And we have this homework 7, which is available already. I'm showing here in the shared folder. It's already available in the server as well. You can, if you're using server, still get it from the server. If you are using in the local machine, just download it from this shared folder. You have project tree here. You have homework 3, which is the deadline. Sorry, homework 6, the deadline is on this Friday midnight. Okay, clear? So we done for today class, But if you're wishing to work together, I can divide this class. I mean, I'm going to basically not be available. If you're wishing to work together for the homework 6 that I have here, I can just, if you want to stay here, I can divide those students that they want to work together in a groups of 2 or 3 so they can work together for another 1 hour. But if you want to finish the session, it's up to you. So if you're finished, you can just leave the session. If you're staying, I'm going to divide you to work together. If no, you can just work on your own. It's totally fine because we are done with today's class. Slides.